Monoidal categories and their representations, Lecture 10. Problem session. Problem 1. Let G be the cyclic group of order 2, which means that G consists of two elements, E and S. E is the neutral element, and S squared is equal to E. Let K be an algebraically closed field. Let K triv be the trivial G module, and let P be the indecomposable projective cover of the trivial G module. Show that P is a self-dual object of the tensor category G mod of all finite-dimensional G modules. Compute the tensor product of P with itself over K, and determine, as a G module, the kernel of the adjunction morphism from this tensor product to K triv. Also determine the composition of the previous adjunction morphism after the other adjunction morphism from K triv to the tensor product of P and P. And before we will start solving this problem, the usual warning. Of course, one should expect that both the solution and the answer to this problem will depend on the characteristic of our field, K, because we are talking about a finite group and its representation theory over this field. So let's solve this problem. Assume first that the characteristic of K is different from 2. 2 is the only prime number which divides the order of our group. The order of our group is 2. So 2 should be the only special characteristic. So let us first assume that the characteristic is not 2. Then, by Maschke's theorem, G mod is a semi-simple category. In particular, every simple object is projective, and this means that our projective cover P of the trivial G module K triv is actually isomorphic to K triv. And of course, the trivial G module is the identity object of our monoidal category G mod. And for the identity object, it is very easy to guess the adjunction morphisms for the pair consisting of the identity object and the identity object. So the identity object is adjoint to itself. Namely, as the counit of the adjunction, epsilon, we can take the morphism from K triv, tensor K triv to K triv, which sends 1 tensor 1 to 1. And the unit eta of the adjunction will go from K triv to the tensor product of K triv with itself, sending 1 to 1 tensor 1. It's obvious that these two maps are homomorphisms of G modules. Let us now check the first adjunction axiom for the adjoint pair x, y. So starting from x, we apply the inverse of the right unitor to go to x tensor the identity. Then we use eta to go to x tensor y tensor x. Then we change the bracket using the associator. Then we use epsilon on x tensor y to go to I tensor x. And then we use the left unitor to go to x. In our case, x is equal to y and is the trivial G module. And all our maps are given by sending 1 to 1 tensor 1. So we start with 1, we go to 1 tensor 1, then we go to 1 tensor 1, then we change the bracket going to 1 tensor 1, then we collapse this to 1, and then we collapse this to 1. So the composition of these maps is obviously the identity. This verifies the first adjunction axiom, and the second adjunction axiom is verified similarly. In particular, it follows that the trivial module, the identity object of our category, is self-adjoint. And also from the explicit form of the adjunctions, we see that both adjunction morphisms are isomorphisms. In particular, the kernel of epsilon is 0 because epsilon is an isomorphism, and the composition of epsilon after eta is the identity map because it starts with 1, goes to 1 tensor 1, and then collapses it back to 1. Okay, so this completes the case of characteristic different from 2. Now let's assume that the characteristic of our field is 2. In this case, the group algebra of our group contains a non-zero nilpotent element, namely the element E plus S, where E is our identity in the group and S is our non-identity element in the group. Let's denote this element by X. Then X squared is equal to E plus S squared, which is equal to 2 times E plus S. And since we are over a field of characteristic 2, this is equal to 0. In particular, the group algebra of our group is isomorphic to the algebra of dual numbers over K. So it's the truncated polynomial algebra when we take the polynomial algebra K of X and divide by the ideal generated by X squared. Let's denote this algebra by A. So this is the algebra of dual numbers over K. This algebra is local. Of course, it has a unique maximal ideal generated by X, and so it has a unique optoisomorphism simple module. We know that this is just a trivial G module, and then a unique optoisomorphism in decomposable projective module, namely the regular module. So our projective cover P of the trivial module is the regular module over our group. And it is very easy to check that the simple module and the projective module are the only indecomposable A modules for this very small algebra. Exactly the same proof as before shows that the trivial module is self-adjoint. So it's both left and right adjoint to the trivial module as an object in our tensor category. Since the regular module is the only remaining indecomposable, it also must be self-adjoint, which is exactly what we wanted to prove. So the projective cover, the indecomposable projective cover of our trivial module is a self-adjoint object in our tensor category. Next, we need to discuss the tensor product of the projective cover P with itself. In other words, we need to discuss the tensor product of the regular G module with itself. And the claim is that this is isomorphic to the direct sum of regular G module with itself. Note that the dimension on both sides is 4. So 2 times 2 is equal to 2 plus 2. So in order to prove this isomorphism, we just need to check that the left-hand side is actually a projective module, because then each projective can be written up to isomorphism uniquely as a direct sum of projective modules. And there is only one projective module of dimension 4 in this case. Let us look at the functor of tensoring with the regular G module. So we just established that this functor is biadjoint to itself. So in particular, it is exact because it has both left and right adjoint. But this means that it is left adjoint to an exact functor because it's adjoint to itself. And any functor which is left adjoint to an exact functor sends projectives to projectives. So if we have a functor f which is left adjoint to an exact functor g, then f sends projective objects to projective objects. Indeed, if x is a projective object, then homing from fx somewhere, because of the adjunction, is isomorphic to homing from x into g of this something. But g is an exact functor and x is a projective object, so homing from x is an exact functor as well. This means that the right-hand side is an exact functor, which means that the left-hand side is an exact functor, because this is an isomorphism of functors. But this means that fx must be a projective object. So this completes our proof that the tensor product of the regular module with itself is isomorphic to a direct sum of the regular module with itself. So 2 times 2 is equal to 2 plus 2 here. Okay, so the indecomposable module P has dimension 2, in particular it has length 2 because the simple module is one-dimensional, and it has simple top and simple socle, and they both are isomorphic to the trivial G module. The map eta, the unit, it starts from a trivial module and goes to kg plus kg. And so the image of eta must belong to the socle of kg plus kg. At the same time, epsilon, it goes from kg plus kg to the trivial module, so it must kill the socle of kg plus kg. This means that the composition of epsilon after eta is the zero map in this case. The counit map epsilon, itself is not 0 because of the adjunction identity. So if it were 0, we can write a junction identity, and then in the middle we will have this counit map evaluated at some object. So it must be a 0 factor of the identity which we will get using the adjunction axiom. So this is impossible. This means that the adjunction map is non-zero. But the image is a trivial module, so it is surjective. So in particular, the adjunction map is indeed a projective cover of the trivial module, but not an indecomposable projective cover. So the kernel of this map will be the direct sum of the kernel of the indecomposable projective cover of the trivial module and the additional projective module in our projective cover here. In other words, the kernel of epsilon as a G module is a direct sum of the regular G module and the trivial G module. And this completes problem 1. Problem 2. Classify all square matrices M with positive integer entries which satisfy the equation that M squared is equal to 3M. Solution. Let M be an n times n matrix with positive integer entries satisfying the equation M squared is equal to 3M. So let the entries of this matrix M be mij's. So I is between 1 and n, and j is between 1 and n. So this is a matrix with positive integer entries. So we can apply Perron-Frobenius theorem to this matrix. So let lambda be the Perron-Frobenius eigenvalue of M. By assumption, the matrix M is annihilated by the polynomial x squared minus 3x. Therefore, the Perron-Frobenius eigenvalue lambda must be a root of this polynomial. So lambda squared minus 3 lambda should be 0, which means that lambda is equal to either 0 or 3. But we know by the Perron-Frobenius theorem that the Perron-Frobenius eigenvalue is positive. Therefore, it cannot be equal to 0. So the Perron-Frobenius eigenvalue of M is equal to 3. Also note that our polynomial f of x, x squared minus 3x, it doesn't have multiple roots. It has 2 roots and they both are simple. But this means that our matrix, which is annihilated by this polynomial, our matrix M, must be diagonalizable. So, if our matrix M has only one eigenvalue, which is lambda is equal to 3, then M must be equal to 3 times the identity matrix. And all entries of M are positive. This means that the only possibility is that M is equal to the 1 times 1 identity matrix 3. Next, assume that M also has eigenvalue 0 with some multiplicity k, which is greater than 0. We know that the Perron-Frobenius eigenvalue has multiplicity 1, so we have lambda is equal to 3. This is an eigenvalue with multiplicity 1, and the eigenvalue 0 has multiplicity k. So n, the size of our matrix, is equal to k plus 1. The trace of our matrix is just the sum of all eigenvalues, so this is 3 plus k times 0, so this is 3. And the trace of our matrix is the sum of the diagonal elements. And there are only 4 ways to write 3 as a sum of positive integers. So we can write 3 as 3, or as 2 plus 1, or as 1 plus 2, or as 1 plus 1 plus 1. So which means that the diagonal of M is either 3, or 2, 1, or 1, 2, or 1, 1, 1. And in the first case, if the diagonal is 3, we get the situation which we already discussed. This is a situation where k is equal to 0, which is excluded by our assumption. This case we already discussed before. Now let us consider the second case. The diagonal of M is 2, 1. Then we can write the matrix M as 2ab1, where a and b are some positive integers. The equation that m squared is equal to 3m is then equivalent to the following system of equations. So for the 1, 1 entry, we will have the equation 4 plus ab is equal to 6, and for 2, 2 entry, we will have the equation AB plus 1 is equal to 3. And for the other entries, the equations will be 3a is equal to 3a, and 3b is equal to 3b, so no real condition. So this system of equation is equivalent to one equation, ab is equal to 2, and ab are positive integers. So we only have two solutions, ab is equal to 2, 1, or ab is equal to 1, 2. Therefore, we have only two matrices with this diagonal, the matrix 2, 2, 1, 1, and the matrix 2, 1, 2, 1. Similarly, in the third case, where we have the diagonal 1, 2, the matrix M is one of the following two matrices, 1, 2, 1, 2, or 1, 1, 2, 2. It remains to consider the last case, case number 4, and this is where the diagonal is 1, 1, 1. So M is a 3 times 3 matrix. Let us note that the matrix M has rank 1. It's a diagonalizable matrix, which has a unique non-zero eigenvalue, and this eigenvalue is simple. And then you have eigenvalue 0 with multiplicity n minus 1. So the rank of this matrix is 1. So all rows of this matrix must be linearly dependent, so they all must be proportional, and similarly all columns must be proportional. If we would have some off-diagonal element of this matrix which would be different from 1, let's say it's an element A in row I and column J, J is different from I, then we take row I and divide it by A, we should get row J, because row J has 1 in column J. But this is of course not possible because row I has the diagonal entry 1, so it's the entry in column I, and this is not divisible by A. So this is a contradiction. Therefore, all entries of M are equal to 1, and M is just the matrix 1, 1, 1, 1, 1, 1, 1, 1, 1. And now we can just collect the answer. Here are the possible matrices M, which square to 3 times itself. It's a matrix 3, the matrix 2, 2, 1, 1, 2, 1, 2, 1, 1, 2, 1, 2, 1, 1, 2, 2, and 1, 1, 1, 1, 1, 1, 1, 1, 1. Problem 3. Consider the associative algebra D of dual numbers over C. So D is a quotient of the polynomial algebra Cx, modulo the ideal generated by x squared. There are only two indecomposable left or right D modules, namely the indecomposable projective module D and the simple module given by D divided by the radical of D. We already mentioned it in our solution to problem 1. Let curly D be the additive closure inside the monoidal category of all DD bimodules, which is generated by all DD bimodules of the form X tensor Y, where X is a left D module and Y is a right D module, together with a regular DD bimodule D. Show that curly D is a monoidal subcategory of the category of DD bimodules. Determine the left, the right, and the two-sided cells of curly D, and compute the split Grothendieck ring of curly D. Determine whether this category curly D is rigid, and determine whether this category curly D is braided. Solution. For any DD bimodule B, if we tensor B with the regular bimodule on the left or on the right, we will get B back. So we will not leave the additive closure of B. Further, if we have two left D modules X and X prime, and two right D modules Y and Y prime, then tensoring over D, the bimodule X tensor over Cy, with the bimodule X prime tensor over Cy prime, we can of course rearrange the brackets in this tensor product because of the associativity, and then we will get on the left-hand side X, on the right-hand side Y prime, so we will get the bimodule X tensor over Cy prime, with the multiplicity given by this middle vector space, Y tensor over Dx prime. So we will get a direct sum of many copies of X tensor Y prime, and the number of copies will be the dimension of the vector space y tensor over d x prime. Now, if we combine these two facts with the observation that the tensor product is biadditive, we see that our category Carly D is invariant under the tensor product. So the first thing says that with a regular bimodule, if we tensor, we never leave any additive closure. And the second line says that the bimodules of the form left module tensor right module, when tensored with each other, produced bimodules of the same sort, up to some summons. By construction, the category Carly D contains the identity object inside the category of all bimodules, and so it follows that it is a monoidal subcategory of the category of all DD bimodules. Let us denote by L the simple module given by taking the regular module D and factoring out its radical. So since these commutative left and right modules are the same, so by definition, the indecomposable objects in the category Carly D are the regular bimodule D, and then the tensor product of L with itself, the tensor product of D with L, the tensor product of L with D, and the tensor product of D with itself. Now we want to take a look at this formula when we tensor two bimodules of the form left module tensor right module. We keep the left part, the right part, and we have the multiplicity given by this vector space. So let's compute these multiplicity vector spaces between L and D. If we tensor L with itself over D, we will get L. If we tensor L with D over D, we will get L for obvious reasons, regardless of what the order of the factors is. And when we tensor D with itself over D, we will get, of course, D. Note that here we have the two-dimensional vector space, while here we have one-dimensional vector space. Therefore, the multiplication table for the standard basis in the split Grothendieck ring, and the standard basis is given by the classes of indecomposable modules, is given by the following table. So we have D, L tensor L, D tensor L, L tensor D, and D tensor D, and we multiply with itself. So D is the identity, so the first row and the first column, they're just given by taking D to be the identity element. And then L tensor L times L tensor L is L tensor L. L tensor L times D tensor L is L tensor L. Multiplicity is 1 because L tensor over DD is L. It's one dimensional. Similarly, L tensor L times L tensor D gives you L tensor D. So left part comes from here, right part comes from here, and the multiplicity comes from here, 1. And similarly the rest. So we always take left part here times right part here, and the multiplicity is almost always 1, except for these 4 exceptions where we have D hitting D. So we need to use this isomorphism, and here D is a two-dimensional space, so we get multiplicity 2 here. So this happens in this product, in this product, in this product, and in this product. So this is the multiplication table for the split Grothendieck ring of our category Carly D. And we can use this multiplication table to read off the cells. So the left cells, so these are elements which we can get from one another using left multiplication as summons. So if we start from D, we can go to everything using left multiplication, but then if we get something which is not D, we can never come back. This means that D is a left cell on its own. Starting from L tensor L, we can change the left component to D, but that's it. And starting from D tensor L, we can change the left component to L, but that's it. This means that L tensor L and D tensor L form a left cell. Similarly, L tensor D and D tensor D form a left cell. So we have 3 left cells. Similarly, we have 3 right cells, D, and then L tensor L and L tensor D. So we can change the right component by right multiplication. And D tensor L and D tensor D. Again, we can change the right component by right multiplication. For two-sided cells, we need to unite left and right cells, and we will get only two two-sided cells, the cell D, and then the remaining cell consisting of all other elements, L tensor L, L tensor D, D tensor L, and D tensor D. So here is the egg box diagram of these cells. So we have the two-sided cell consisting of D, and then we have here the two-sided cell, which is a union of two left cells and the union of two right cells. The left cells are columns and the right cells are rows. We have four elements arranged into two left and two right cells. Great. Let us now discuss rigidity of Carly D. If Carly D were rigid, then tensoring on the left or on the right with any object of Carly D would be an exact endofunctor of the category of all DD bimodules. At the same time, if we have a DD bimodule, we know that the endofunctor of the category of all D modules given by tensoring with this bimodule on the left, this endofunctor is exact if and only if our bimodule is right projective. In our category Carly D, we have the bimodule L tensor L, which is manifestly not right projective. Therefore, we automatically get that tensoring with this bimodule is not an exact endofunctor of D mod. And then we claim that it's not an exact endofunctor of D mod D either. To prove this, take an exact sequence, so 0 goes to the simple module, then to the projective, and then to the simple module, and then to 0. So this is an exact sequence in D mod. We can make it into an exact sequence in D mod D by tensoring on the right with a simple right module L. So we have an exact sequence in the category of bimodules when we start from L tensor L, embed it into D tensor L, and then project it back on L tensor L. So this is an exact sequence in D mode. If we now apply our tensoring with L tensor L on the left to this sequence, we will get a sequence where the first component is L tensor L, the second is L tensor L, and the third is L tensor L. It doesn't matter what the maps in this sequence are, it has no chance to be exact, because all three non-zero components here are one-dimensional. It is not possible that the sequence is exact. Therefore, tensoring with L tensor L is not an exact endofunctor of the category of bimodules, which means that Carly D cannot be a rigid category. Finally, what about braiding? If the category Carly D were braided, then the split Grothendieck ring of Carly D would be commutative. But it is not commutative. So for example, if we multiply L tensor L with D tensor L, we will get L tensor L. If we multiply D tensor L with L tensor L, we get D tensor L. These are two different things, non-isomorphic objects in our category. So the Grothendieck ring is not commutative, and hence our category cannot be braided. This completes problem 3. Problem 4. Determine the Drinfeld center of the monoidal category set of all finite sets, where the monoidal structure is given by the Cartesian product. Solution. Let x, phi be an element of the Drinfeld center of our monoidal category set. The identity object in this monoidal category is some fixed singleton. Let this singleton contain the element star. So this is the identity object. Then we have the map phi evaluated at our singleton I. This should be a bijective map from x times star to star times x. So this must be given by some bijection sigma from x to x, so that phi evaluated at the identity sends x comma star to star comma sigma of x. So there is some bijection from x to x with this property. Now let y be a finite set and little y a fixed element of our set y. Consider the function f from our singleton star to y, which sends star to our element little y. So we have the naturality of phi in y. This means that we have the following commutative diagram. If you start from x times star, we can use phi I to go to star times x. From x times star, we can use identity times f to go to x times y. Using phi y, we can go to y times x. And to y times x, we can also arrive from star times x using f times identity. This diagram should commute because of the naturality in y of our phi's. One way around this diagram, since x comma star, using phi I to star comma sigma of x, and then using f times the identity to y comma sigma of x. The other way around, if we start from x comma star, we go to x comma y, and then phi y applied to x comma y. So this means that phi y sends x comma y to y comma sigma of x. So this we derive from the naturality of phi in y, from the commutativity of this diagram. And now let us look at the Greenfield center axiom. So we have this axiom that starting from x tensor y and then tensor z, we can go to y tensor z tensor x in two different ways. We can rearrange the bracket applying the associativity. We use the Greenfield center thingy, and then we use the associativity again. Alternatively, we use the Greenfield center thingy internally in the bracket, then we use associativity, and then we use the Greenfield center thingy again. It is interesting to note that one way around uses phi only once, and the other way around uses phi twice. So if we start from a particular element x, y, z, one way around will send it to y, z, sigma of x, while the other way around will send it to y, z, sigma square of x. Since this diagram must commute, we get that sigma should be equal to sigma squared. This implies that sigma is the identity map on x. In other words, phi sends x, star to star, x, and hence it's coincide with the symmetric braiding on our category sets. Consequently, the forgetful functor from the Greenfield center to set is an equivalence of braided monoidal categories. And this completes problem 4. Some additional problems and questions. Question 1. Let A be the path algebra of the quiver with two nodes and one arrow between them. Over some field K. Compute the split Grothendieck ring and all cells of the monoidal category of AA bimodules. Question 2. For the same A, determine whether the category of all AA bimodules is rigid. Question 3. For the same A, determine whether the category of all AA bimodules is braided. Question 4. Classify all square matrices with non-negative integer entries which satisfy the equation that m squared is equal to 3m. Question 5. Describe the Greenfield center of the monoidal category of all finite S2 acts, which means actions of S2 of the symmetric group S2 on finite sets, where the monoidal structure is given by the Cartesian product. Thank you very much and see you next time.